Thank you. Thank you. Thank you. It's not about me. That's you. That's you. Why we're here. All right. So we're going to continue to talk about probability. In the past, we've talked about two special kinds of events where we have some calculation rules for calculating combinations of those events. We talked about mutually exclusive events where there's no overlap in the outcomes. And for those events, we can calculate the probability of A or B as just the probability of A plus the probability of B. For independent events, A and B, we can calculate the probability of A and B by taking the probability of A and multiplying it by the probability. So today we want to ask, what happens when we don't have events that are independent, or we don't have events that are mutually exclusive, but we want to calculate these probabilities of combined events? So the first one is called the general multiplication rule. And the general multiplication rule is used whenever you want to calculate the probability of A and B, and you don't know whether the events are independent or not. And the formula comes from the formula that we introduced for conditional probabilities. We said that the probability of A given B is equal to the probability of A and B divided by the probability of B. So this was our definition of conditional probability. But we can also rearrange this formula to solve for the probability of A and B, and we get the general form of this as the probability of A and B is equal to the probability of B times the probability of A given B. And this gives us our general form for the probability of A and B. Now, if you recall, for independent events, right, the idea of independent events are that the outcome of one event has no impact on the other. So if A and B are independent, then the probability of A given B is just going to be the probability of A. And so we would get the probability of A and B is equal to the probability of B times the probability of A, which was our formula for independent events. Now, what about the case for ORs? So this is the general addition rule. And the general addition rule says that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So let's think about what this says and visualize this using a Venn diagram. So if this is event A and this is event B, then the overlap here is A and B. And so if we were to calculate the probability of A or B and use the formula that we've previously introduced, the probability of A plus the probability of B, then the probability of A is going to include everything in this circle, including the overlap. But the probability of B is going to include everything in this circle, including the overlap. And so you'll notice that whenever we do that, this overlap has been counted twice. And so to adjust for that, we just subtract the probability of the overlap. And just like before, if we have the special case that we've talked about in the past, where we have mutually exclusive events, remember the idea of mutually exclusive events are events that have no outcomes in common. And that means that the probability of A and B is always 0. So if the probability of A and B is 0, then this subtraction term is just 0, and we're left with just the probability of A plus the probability of B, which was our original formula. So let's use these two formulas in an example. Okay, so some studies have shown that for women who live to be at least 90 years old, they have a 1 in 7 chance of developing breast cancer. So let's let B be the event of develop breast cancer. And let's consider a particular test for breast cancer that for women who develop breast cancer, that test comes back negative 2% of the time. So what we're saying is that this gives a false negative 2% of the time. So let's let N be the event of a negative test result. And then let's say that if we just randomly sample women, this test will give a negative test result 85% of the time out of the general population. And let's see what we can tell with this information. So the probabilities that we've talked about so far are the probability of a randomly selected woman who lives to be 90, for them to develop breast cancer, we said was about 1 in 7, so that's about 14.3%. We also said that the probability of getting a negative result for a woman who will develop breast cancer is 2%. So that's a conditional probability. Because we know that the woman in question is going to develop breast cancer, we know that B has occurred. And so we're saying that the probability of getting a negative test result, given that the woman is going to develop breast cancer, is 2%. And then lastly, we have the probability of getting a negative test result in itself is 0.85. So here's some starting probabilities that we can work with. All right, so using this, we can ask, what is the probability of a woman getting a negative test result and having breast cancer? So we can ask, what is the probability of B and N? Now, if we were to know that the probability of getting breast cancer and getting a negative test result were independent, then we could just apply the independence formula to calculate this probability. But we don't know that. So we have to use the general rule for this. And so that means that this probability is equal to the probability of B times the probability of N given B. And so this is the probability of B, we said was 0.143. And the probability of N given B is 0.02. And so if we pull out a calculator, we get that this is equal to 0.0028. So that's a pretty low probability. But let's ask, what's the probability of B or N? So we're asking, what's the probability of having breast cancer or getting a negative test result, or both, right? So we said this is going to be the probability of B plus the probability of N minus the probability of A, or not A, of B and N. So our probability of B is 0.143 plus our probability of N is 0.85, and we can subtract away the probability of B and N, which is 0.00286. And again, getting out a calculator, we have 0.143 plus 0.85 minus 0.0028. Gives us 0.99014. So let's stop for a second and think about what that number means. 99% of women, or there's a 99% chance that a randomly selected woman would either test negative or have breast cancer. And so what is left out of the probability of having breast cancer or getting a negative test result, or both, is the probability that it's someone does not have breast cancer but tests positive. And so there's still 1% chance of a person getting a positive test result, even though that they don't have breast cancer. And this is a major issue in the medical industry, is making sure that whenever you have tests, that those tests are as accurate as possible, because the stakes are so high, right? We have 2% chance of someone who has breast cancer getting a negative test result. And we have a 1% chance of a woman who does not have breast cancer being told that she does. And so a lot of work goes into these tests is to making sure that these errors are as small as possible. Now let's ask ourselves, can we make any claims about the probability or about the event of developing breast cancer and getting a negative test result? Maybe we didn't need to use these formulas. Maybe we have special cases. Maybe they're independent. Maybe they're mutually exclusive. Right? So let's ask the first question, whether or not they're independent. Right? If they're independent, then what that means is that my probability of getting a negative test result should not change given whether or not the person is going to develop breast cancer or not. But we know that the probability of N is equal to 0.85, and the probability of N given B is equal to 0.02. These are very different, right? So this is not equal, so these are not independent. And that's exactly what you would want. You would be concerned if your likelihood of getting a negative test result was completely independent of whether or not you were going to develop breast cancer, right? But let's also ask, are they mutually exclusive? Right? What does it mean to be mutually exclusive? It means that the intersection has no probability of happening, right? That the probability of B and N can't happen, right? But we just said that there's a small but positive probability of developing breast cancer and getting a negative test result. So these are also not mutually exclusive. So these are the types of probabilities that we can now calculate without knowing whether or not we have the special case of independence or mutually exclusive. Furthermore, using this data, we can answer the question of, are events mutually exclusive or are they independent? So if you're not being told that you're in one of these special cases, you need to default to the assumption that you're not and use these general formulas.